Now we move on to part 4, where we discuss the methods of solutions to the partial differential equations in this course. In this course, we construct solutions, but we do so quite concretely with definite formulas as opposed to using abstract or indirect methods of proving the existence of the problems. So let's start. One of the fundamental tools that we use for both the Laplace equation and the heat equation is fundamental solutions. So let's describe the idea for the Laplace equation. We know that the Laplacian, the operator, has many symmetries. In particular, it's rotationally symmetric, it's translationally symmetric, so you can translate a solution and you still have a solution. You can rotate a solution and you still have a solution. You can rescale a solution and still have a solution, and so on. And because of this, we might want to understand what are the radially symmetric solutions. So the solutions which only depend on the distance from a certain point and not on a particular location in space. Okay. So we can already, you can, of course, just write down what the differential equation is in polar coordinates and then solve this, which is the solution in the script. But we can already start to think about what the solution to a radially symmetric solution would have to have. So the first thing to think about is that it would have to be monotonic in the radius. Okay, so if we try to draw a little cross section here or a little picture, if you have a point, so it's radially symmetric like this, and if it increased and then decreased, what you would have here is a local maximum. Okay, so if you have any point whereas when you move in the r direction, it goes from increasing to decreasing in the radial direction, then because of the symmetry, the radial symmetry, you would have a local maxima. And we already know that harmonic functions do not have local maxima. So therefore, it has to be monotonic. Like so. And in particular, we know from exercise 13 that, or more generally from the mean value property, that on every ball enclosing 0, the integral on the sphere has to be the same, right? Because we know by the mean value property that increasing the spheres does not change the value of the integrals, the mean integral over that sphere. So if that's to be constant, then we know this function actually has to be decreasing as you increase the radius, right? So the value of the function decreases as the sphere gets larger so that the total integral stays the same. Okay, so we know we have to have a decreasing function in the radius, a monotonically decreasing function in the radius. And so then we suppose that at the origin, if it was some finite value, then we would have a finite value, and then from then decreasing, that would give us a maximum of the function as well, and that is also forbidden. So we can conclude from this that the only possibility for a non-constant radially symmetric solution has to have a singularity at the origin. And then when we go through and we solve the equations, that's exactly what we see. It depends a little bit on the dimension, what sort of singularity we have. For 2 dimensions, we have a logarithmic singularity at the origin. And for higher dimensions, we have a polynomial singularity where the order of the polynomial is 2 less than the dimension. One way to understand this is that for dimensions greater than 2, this is the typical behavior. But if you try to look at n equals 2 for this formula, we have a divide by 0 here, and we have an x to the power of 0 here. That's exactly what you see when you take an integral, when you integrate, like, for example, e to the n or e to the k for k equals -1, and you try to apply that formula, you get a divide by 0 and a power of 0. And so that's exactly why we see the logarithm occurring in dimension 2. In dimension 1, all harmonic functions have to be linear, and so there's no possibility for a radially symmetric solution. So we treat n equals 1 as a separate case because the equation is so simple to solve there. It just becomes an ordinary differential equation. Okay, so that gives us these fundamental solutions for the Laplace equation. Our approach is slightly different in the heat equation. Instead of looking for radially symmetric solutions, we look for solutions that are radially symmetric in the space coordinate, but in the time coordinate, we see we have this certain invariance of solutions. Right? So if you have a solution to the heat equation and you scale it in the right way, then you end up with another solution of the heat equation. And so we look for a solution of the heat equation which is constant on these characteristics that sort of that typify this scaling. And in this case, we end up with a two-dimensional family of such solutions, and we choose the constant so that it vanishes at infinity. We choose the constant so that the fundamental solution of the Laplace equation also vanishes at infinity. It has a positive singularity at the origin, and it decreases monotonically to 0 at infinity. And we know it's the constant is chosen so that the integral on every ball is 1. Right? That's how you get these leading constants here. In the case of the heat equation, you also choose it so that it vanishes at infinity. The constant vanishes at infinity. And instead of normalizing over balls, you normalize over slices of constant time. So for a fixed time, you have all the space variables, and the integral over that should be equal to 1. Okay. You see from the characteristics that the characteristics all meet at t equals 0. They all come together. So that's why we only consider positive time initially for the heat equation for this. And we get this formula on the top line here, t greater than or equal to 0. But there was actually an exercise. Yes, exercise 34a. You take the fundamental solution of the heat equation, and you show that it actually extends to t equals 0 to be identically 0 at that point, and all its derivatives are also identically 0. So except for the point where this is equal to 0, then you have a problem. So what happens for x not equal to 0 is that this exponential factor dominates the divided by t factor here, and everything goes to 0. And so in that spirit, you can extend it to a smooth function that is 0 for negative t, and t equals 0 except for the origin. Yes, and so this has the nice behavior then from this normalization here that on every constant time slice, it's equal to 1, that this is actually a family of modifiers, right? So convolving with these gives you, as t goes to 0, the function back. And that's the main content of lemma 4.3. Okay, so what do we use fundamental solutions for? Fundamental solutions are used for having a solution to the inhomogeneous equation. All right, and so we know that if you have a solution to the inhomogeneous equation, you can add any other homogeneous solution. So in the Laplace equation, this would be a harmonic function, or a solution to the homogeneous heat equation and get another one. So fundamental solutions, we could have taken different normalizations and then had different fundamental solutions and then had different solutions to the inhomogeneous problem resulting. But the way that we've chosen it is that the fundamental solutions we have in this previous question obey the fact that when you apply the differential operator to them, the partial differential operator, you get the delta distribution. Right? This is essentially what is proved in theorem 3.2. There's a comment, I believe, after theorem 3.2 that says this, and also in theorem 4.4, and then explicitly in exercise 34 as this distribution heat. It is an explicit part here. Part F, E, F, and G together show that it is equal to the delta distribution. why is that a useful property? It's a useful property because of the following reason. If we want to solve the inhomogeneous problem, what we can do is we can look at the differential operator of the fundamental solution convolved in convolution with the inhomogeneous term. Now for L, which is a linear partial differential operator, we know from this property that the partial derivative of a convolution is just the partial derivative of one of the functions convolved with the other. This extends to linear partial differential equations with constant coefficients to give us the partial differential operator applied to the fundamental solution convolved with f. By our choices, the fundamental solution obeys the fact that is the delta distribution, and the delta distribution convolved with any function just gives that same function again. So what we have is we have that this function u, the convolution of the fundamental solution with the inhomogeneous term, gives the solution of the inhomogeneous equation, namely L of u is equal to f. Okay, one small point here is we define the inhomogeneous equation for the Laplace operator as negative of that is equal to f. If you're going through these proofs, be aware of this because otherwise you will have some slight differences in sign in different places. So that's one thing to be careful of. For the heat equation, there is no such problem. All right, because we write this with the negative sign already. Okay, so this is already very useful. If you can find a fundamental solution, then you can find a solution to every inhomogeneous problem, no matter what the function f is. All right, this is great. Okay, let's make a comment about how you actually prove this. All right, because you need to prove this relation here. All right, what we just found is we found solutions that were radially symmetric, but they're not defined at 0, and this is not defined at 0, 0 either. So either you have to prove that in the sense of distributions, the fundamental solution obeys this relation with the delta distribution, and this is quite a bit of work. For example, we'll see how you would do this in exercise 35. Or what you can do instead is you can just take this idea and write down what you think the solution should be, namely the convolution of the fundamental solution and the inhomogeneous term, and then just prove directly that the function you define in this way does solve the inhomogeneous partial differential equation. And this is the approach taken in the proofs of this course. It just writes down, using this idea, it writes down what the function or the solution should be, and then checks directly that this does solve the partial differential equation as claimed, without worrying about distributions so much, or worrying about distributions. So how does it do this? The main problem is that the fundamental solution does have a singularity, right? That's not so much a problem for defining the integrals because it's only 1 point, so that doesn't change the definition of the integral so badly. But to prove some sort of convergence results or something like this, you do need to do some analysis. And the way to do this is typically split it up into a ball that surrounds the singularity, a ball of, say, at radius epsilon, and a part away from that ball. So if we look in the proof of, here we have theorem 3.2. We have, as you can plainly see here, the convolution of the fundamental solution with f, the inhomogeneous, and you can see this minus sign I warned you about. And what we do is we check that this does obey Laplace's equation by trying to calculate the Laplacian of this defined function, and we split it into two parts: a part I epsilon over a ball that's near 0, and a part j epsilon over a ball that's away from 0. and you just you have to do estimates for each part to show that they're small in the limit that epsilon goes to 0. So here you show that there's two different formulas depending on the dimension, because the two different formulas for the fundamental solution depending on the dimension. But in both cases, when epsilon is small, this tends to 0. So the part near the singularity tends to 0. And then the part away from the singularity, you break up into something that is 0 and something on the boundary, because we know from the mean value principle that the spherical mean is going to have some nice property. So it's good to look at the boundary of a sphere. And that's exactly how it goes. Oh, no, it's not. It proves here that L goes to 0. It's still nice, and you still do use this property that the integral is constant, but it goes to 0, and then this part is the part that you use to get back f, and that this solves. So that's how you typically do the proof. If you want to prove that the fundamental solution is equal to the delta distribution, you more or less do the same thing. You just have to worry about having distributions, and you always have extra functions, extra test functions around to help you not have to integrate over all of Rn. You only have to integrate over the domain of the test function. But you still have to do very similar calculations. So maybe it's more direct to go this way, but more useful to prove this one. Okay. So that solves inhomogeneous equations, but inhomogeneous equations on all of Rn, basically. If you look at this definition of theorem 3.2, you have the Poisson equation of all of Rn here. We're actually more interested in the Dirichlet problem, which of course requires boundary value conditions. So the idea of Green's function is to extend fundamental solutions or generalize fundamental solutions to bounded domains in a way that allows us to do to take into account the boundary value problems as well. So for that, we need a definition of a Green's function. And what I've done here is I put the definition of a Green's function and the heat kernel right side by side with each other, so you can see what is similar and what is different between them. So for a Green's function, we have it's a function of two variables, and the variables are not allowed to be equal to each other. And we have two properties. That g of fundamental solution of x minus y is harmonic, and so in both cases you should think of this this property should hold for all x, but for fixed x. Right? So choose one x and then consider it as a function in y. So the function in y is harmonic, and the function, the Green's function as a function of y is 0 on the boundary. So for y in the boundary of omega. In the same way, the heat kernel is also on x and y in the space domain, not allowed to be equal, but it also allows for a time parameter. Right? So you should think of the heat kernel as being very much like the Green's function, except it depends on time as well. So we have the very similar condition here, that instead of the fundamental solution for the Laplace equation, here we have the fundamental solution for the heat equation, and it should, for every point x and time t, as a function in y, this should solve the heat equation, right? Instead of being harmonic, and the initial condition should be 0 for t equals 0. This should just be identically 0. And then condition 2, it extends to the boundary and is 0 on the boundary. So this condition 1 and 2 is how it is written in the script. You might also want to consider that you just want to make condition 1 here that it solves the heat equation, and 2 is that it's 0 on the boundary and it's 0 initially, right? So it's 0 on the space boundary and it's 0 on the time boundary as well. So that's the definition of the two of Green's functions compared to heat kernels. Okay, so in that case, let's look at property 1 a little bit more. So property 1, what is it really saying? What it's really saying is that it says the difference is harmonic, but what it's really saying is that G, the Green's function, should have a singularity which is like the fundamental solution for when y is equal to x. So it should have a singularity at x, right? So when y approaches x, its behavior should be similar to the fundamental solution as y approaches x. The difference between it and the fundamental solution should be a harmonic function. And we know that harmonic functions are very well behaved functions. So by saying the difference should be a harmonic function, we're saying that the difference should be controlled in some way or some very nice thing. And so, G should have a singularity like the fundamental solution. And we see the same thing here. All right, that the difference when y approaches x, for example, y approaches x here, then x minus y approaches 0, and we know we have some, we have some singularity at t equals 0, x space equals 0 for here. So why is it important that the Green's function have a singularity like the fundamental solution? So why it's important is the fundamental solution, we know has a singularity at the origin. What we should imagine, or what we should imagine coming from physics, is that the inhomogeneous equation is heat in the case of the heat equation, or electrical charge in the case of Laplace's equation. So I don't think we've mentioned this, but the Laplace equation describes an electric field around some electrical charges. So the inhomogeneous term in the Laplace equation, these are the electrical charges. All right, so this might be the electrons producing the electric field U, for instance. And in the heat equation, U is the temperature, and F is here a heat source that's being applied to the domain. All right, so like a flame or a cooling source or something like this. So what the fundamental solution is if you imagine it's the electric field corresponding to a single point charge, so a single electron, or it's the temperature that results in a body if you just heat the body at one single point with a constant amount of heat. So in that respect, the solution to the inhomogeneous problem is that then if you have multiple, if you have F, which is not just a single point anymore, you should integrate together all the electric fields coming from the individual point contributions of F. So each point F produces some field given by the fundamental solution, and you should integrate those all together to get the total amount. Or the same thing with the temperature. Each point of heat in the domain produces some amount of temperature, and to get the total temperature of a body, you should integrate together all the temperature coming from individual heat sources. So if we understand the fundamental solution as being the heat generated by a single point source of heat energy, or the electric field coming from a single electric charge, the Green's function should also have that interpretation. All right? It should also somehow be at x that the Green's function is representing an electric field by a charge at x, or it should be representing the temperature coming from a energy source at the point x. So it has this physical interpretation in that case. And so one says that it should have this behavior of the singularity, which is related to this point sources, the same as the fundamental solution. And the fact that it extends to the boundary at 0 is obviously going to be related to the ability of us to solve the equation at 0, to solve the boundary value problem. Okay. So that's sort of giving some interpretation to why property 1 in both cases is important. Okay. It should be important to note that not every domain has a Green's function. So in example, so in exercise 31, sorry, this is again this punctured ball of radius 1 maybe. This domain does not have a Green's function. You can see that from the next slide because we're going to see that if a domain has a Green's function, then the Dirichlet problem is always solvable. And we've seen that the Dirichlet problem is not solvable in this domain, therefore it cannot have a Green's function. So Green's functions are something a little bit special, but when we do have them, then we get very nice results about existence, right? We get this concrete formula to describe the solution. Two properties of Green's function before we move on to how to use them to solve the equations. Though it does have this x and y, and though I have given this interpretation of you should imagine the Green's function as describing the electric field or the temperature field coming from a source at x, it is actually symmetric in x and y, right? Even though we sort of put all these conditions of considering this as a function of y, considering this as a function of y, it turns out that these properties are symmetric in x and y, which is a neat thing, as useful sometimes. And for bounded domains, Green's functions are actually unique. So let's see why that is. So again, whenever we want to prove something is unique, what we should do is we should look at, I don't know, let's call it G tilde, which is suppose that there were two different Green's functions for the same domain. Then we would look at the difference of them, as is typical. Now, what we can do is we can look at G1 minus the fundamental solution of, it's x minus y, minus G2 minus the fundamental solution of x minus y, like this. So we can add and subtract the fundamental solution like this, and then it's this shows you that G tilde is a harmonic function in y, because we know that G1 minus fundamental solution and G2 minus fundamental solution are both harmonic functions in y, and so they're differences as well. And we know that G vanishes for y in the boundary of the domain. And so if we have a harmonic function that vanishes on the boundary of a bounded domain, then we know that this is 0. All right, from, I guess, from energy methods or from the maximum principle. I would probably say the maximum principle. Yeah, so for bounded domains, there's a unique Green's function if there exists one at all. I should say one more thing. How do you find a Green's function? There were several exercises on this. Basically, we know them for the whole space. So for Rn, the Green's function is nothing other than the fundamental solution. So for Rn, there is no boundary. So there is no condition 2 to satisfy. And we can just take the Green's function to be 5x minus y, and then the difference will be 0, which is harmonic. And the same thing, take it to be the fundamental solution of the heat equation. Then the difference will be exactly 0, and so 1 will be satisfied as well in this case. So we know how to satisfy it. We know how to find the Green's function for Rn, and if it's if you have another domain which is related to Rn by a symmetry, so it's a symmetric reduction. So I'm thinking here of the half space or the ball, or then the half space of the ball, so like a hemisphere, or the half space of a half space, which was a quadrant. This is another exercise we did. There is a fairly standard way of producing Green's functions by applying the symmetry to the Green's function of the whole space. Right? Yeah, so revise those exercises to recall that method. In particular, we want the Green's function for balls because we'll use that to get some very nice properties of the functions. So supposing that we do have a Green's function, what we can do is we can look at Green's representation theorem. So Green's representation theorem in the script is 3.16. And if we look there, we have this with the fundamental solution. So we have the fundamental solution of the Laplacian together with Laplacian, and then we have the fundamental solution with some gradient terms over the boundary. But if there exists a Green's function for the domain, you can rewrite it into this form, okay, where you have the Green's function of together with the Laplacian minus u and just the gradient of the Green's function. All right. Notice here in particular, we always integrate in the second variable of the Green's function. So here the second variable is y, here the second variable is z for some reason. Z is just cool, I guess. And the first parameter is always the parameter in the resulting function. All right. So this is sort of how you use the Green's function in a formula, and why it's useful to have Green's functions and heat kernels to be functions of two variables, so you can use them very nicely in this way to get a function of the other variable. So in the same way, we have this representation theorem in 4.16 for the heat equation. So what I should note is that this formula I've written, doesn't apply only to harmonic functions. Okay, it applies to all C2 functions. And this is why it's called a representation formula, because it's showing you a way of writing every C2 function as a particular sum of the integral of a function which is the Laplacian of something plus a term over the boundary. Right? So this is sort of a representation, writing it every function in a particular form. Same thing with theorem 4.16. You write any C2 function as something that is in the image of the heat operator plus some term over the boundary and some term over at time 0. So this applies to all functions. Why this is now useful for solving the boundary value problems is that, of course, if you have a harmonic function, then this term here, the Laplacian, is of course 0, or more generally, this is f. And if it's the boundary, then we usually call this g, all right, g of z. So this gives us a solution in terms of the boundary value and the inhomogeneous term. Likewise here, this is the inhomogeneous term. This here is the boundary term. And this here is the initial term. All right, so we can write this function in terms of these three functions, and this will, of course, obey the partial differential equation and the boundary value conditions. So providing us in the existence of a solution to these Dirichlet problems if we can find a Green's function. So this is very nice because, of course, integrals, while to do integrals by hand is very nasty, they can be numerically approximated very easily. Computers are very good at doing this from a variety of methods. And so you can compute approximate solutions very, very well. And so this answers, for all the domains that we can find Green's functions for, the existence question for PDEs very nicely. So in particular, we mainly do this for balls. All right, so we solve this for balls. Yeah. Okay. So if you're following after the representation formula for the heat equation in the script, then you come to this section, which seems quite different from everything else in the script, about the heat equation in the circle, or S1. What you should understand is the aim of this section is not so much to solve the heat equation on S1, but to solve the heat equation on 0, 1, this closed interval, right? Because one of the typical examples that you want to understand for the heat equation is the heat equation on, say, a metal bar, a metal rod. So you can model this as the domain omega equals 0 to 1, and you control the heat at the two endpoints of this metal rod, and you can heat the interior of the metal rod in some way. And so this is a very typical situation for the heat equation, and that's what we want to get to. And one of the best ways to get to it is through understanding the heat equation on S1. Okay. This section also gives us a little insight into an alternate method of getting to these solutions if you were not going to use the fundamental solution and representation formulas. Namely, this is called Fourier analysis of the problem, and it proceeds like this. So what we saw in exercise 32 about separable solutions is that if you have a solution, say, what am I going to call them? Fk. That is an eigenvalue of the Laplace equation, or the negative Laplace equation in this case. So that means that when you apply the Laplace operator, the Laplacian, to f, you get a constant times f back. All right. If you have such functions, then e to the minus lambda k t fk solves the heat equation. All right. These were what we called separable solutions. And so the idea is that if you can write other solutions as the sum of solutions of this form, then you're in very good shape. You can use this to generate lots of solutions, and in fact, we'll see all of the solutions. So the next thing to think about is that delta, the Laplacian, is a linear operator on the space of functions. And in fact, one of the things you prove in this section 4.7 is that it is a self-adjoint operator on the space of functions with respect to a certain inner product. Why is that is important is because then if you have a self-adjoint operator, all the eigenfunctions or all the eigenvectors for this operator are orthogonal to each other, are perpendicular, with, again, respect to a certain inner product. So this means that there is an easy composition. All functions of the space can be written as a sum of the eigenfunctions of the Laplacian, and it's really easy to figure out how, because you can use the inner product to calculate the coefficients in the orthogonal base. So maybe the idea here, just take a completely trivial example. Just consider the matrix L1, 2. Okay? So obviously it has two eigenvectors, 1, 0, and v2 as 0, 1. And every vector can be written, any other vector, AB. AB is, of course, A times V1 plus B times V2. And now we can understand how L acts on V, because it's just A L acting on V1 plus B L acting on V2. And V1 and V2 are eigenvectors, so this will just be AV1 plus 2BV2. Something like this. So if we can decompose the space, the domain, into a sum of eigenvectors, then we can completely understand what the operator is doing. In general, okay, here I could just see it because it was written like this. If in general we have that v1 and v2 are perpendicular to each other like this, then we know any vector is equal to the inner product of v with v1, v with vi multiplied by vi. If vi are orthonormal. All right, so that means that they're orthogonal to each other and length 1. We have this really simple formula for decomposing any vector into a sum of eigenvectors. And that's exactly what we have in this case. In this case, in section 4.7, we give an inner product. We see that the eigenfunctions are all perpendicular in this inner product, and therefore we get that every function, let's say h, is equal to a sum of eigenfunctions fk, and the coefficients we call h hat. Right, the h hat are the coefficients of this. H hat, of course, is also called the Fourier transform of f. But what it really is doing is it's giving exactly here, it's giving the coefficients in this sum. All right, and it's here we had exactly 2 vectors, so we just take a finite sum. Here we have an infinite number of eigenfunctions, so we should take an integral over all of them. But the idea is exactly the same. All right, let me pull the correspondence. Eigenvector becomes eigenfunction. This becomes this coefficient here. All right. So how does that help us? Well, if we can write h as a sum of eigenfunctions, then we can get a solution where you put, instead of fk, you just put the corresponding solution of the heat equation for that eigenfunction, and you sum over that, and you'll get a solution. And if you look in, this equation right here, this is page 68, what you will see is you have the coefficient h hat here, you have the eigenfunction fk here, and you have e to the negative its eigenvalue times t as the solution. So that's exactly what I have here. You just replace the eigenfunction with the corresponding solution to the heat equation to get a solution of the heat equation. And obviously when t is equal to 0, what do you get back? Nothing other than h. So now this gives a solution to the heat equation with the initial condition h by writing h as the sum of eigenfunctions of the Laplacian. So this is the alternative way to solve the initial value problem, other than the Green's function or the representation formula. What is nice about this is what we can do is we can represent, if we want to model S1, we can model S1 as periodic functions on the real line. Okay, so I think we talked about this a little bit in the tutorial, but S1, we have 2 models. We can either say the function on S1 is a function on 0, 1 with f of 0 equal f of 1, or we can say a function on S1 is a function on R with f of x equals f of x plus 1. That is, it's periodic, it keeps repeating. And these two are equivalent to each other. So why this? When we want to describe functions on S1 in this second form, it's useful to use the Fourier thing. Is that the eigenfunctions fk, I guess x, the e with a positive power 2 pi I k dot x. These eigenfunctions are periodic when k is integer itself. Okay, so when k comes from takes integer values. So if h is periodic, the initial condition is periodic, then it is a sum of the periodic eigenfunctions. Okay, so there's something about eigenfunctions that show when they're periodic very nicely, and so when you want to represent periodic functions, they have nice representations, or they have nice formulas in terms of periodic eigenfunctions, and that's what makes this approach superior for dealing with functions on S1. Okay, so then we come back up to here. And this is exactly what I said. If we have a periodic initial condition, only periodic functions are needed to write it as a sum. Instead of an integral over all values of k, we can just take a sum over the integer values of k, like here. So instead of sum over all k, just a integral over all k, just a sum over the integer k's of the same formula. And then if we write out what this is as an integral and rearrange things, then we have what is inside this bracket here, integrated over this, and we call this the heat kernel here. What's in the bracket? The heat kernel of S1. Okay, so just like we got heat kernels from the fundamental solution and symmetry, if we use this Fourier analysis technique, we can get a heat kernel for S1 when h is a periodic function in a very similar way. And then to handle 0, 1, either you have two approaches. The approach in the script is to do the same thing, but to consider eigenfunctions on 0, 1, for instance, like this, obeying some conditions, and go through the same sort of working, but it's not quite as nice. Or you can do this trick that we discussed in the tutorials, where if you have a function on f1, f is a function on 0, 1, then consider g, which is f of x for x in 0, 1, and f of, how's it going to go? 2 minus x, x in 1, 2. Okay, so g is now a function defined on 0, 2. And you'll notice that g of 2 is equal to f of 2 minus 2, which is f of 0, which is g of 0. So you have, if you take any function f, you can then make this function g, which is periodic by this certain reflection. And now you can solve the equation in the periodic case using what we had up here. And so you use this reflection to get the heat kernel of 0, 1 from the heat kernel of S1. Right? There's an exercise in in the sheets that takes this approach to this, I believe. Okay. Yeah, so that is why we discussed Fourier analysis and the heat equation on S1 to get the heat kernel on 0, 1. And of course, once you have the heat kernel, then the solution is just some integral that you integrate out, and you don't really need to care where it comes from anymore. So that's another nice thing about these representation formulas. They just give you a nice formula at the end to apply. But that's why this section was a little bit different from everything else in the course. Okay, so that covers the methods of solution for the Laplace equation and for the heat equation. So let's move on to the transport equation and the wave equation and other first order systems of equations now. So I've put together the transport equation with the one-dimensional wave equation because the solution of the one-dimensional equation comes from the solution of the transport equation. So let's recall what the transport equation is. It is a first order linear partial differential equation given here. So if we were to write out what this part here bit was, we would have just a sum over some coefficients bi multiplied by the ith derivative in space of u, something like this. And this is the homogeneous transport equation because, of course, it's equal to 0. So in the script, we solve this more or less just by giving the solution, which is of this form. And we will check in a moment that this does actually solve the transport equation. We could also solve it by the method of characteristics, which we'll talk about next. But we can also solve it by a change of coordinates. So, for example, if we have the change of coordinates, swap back to blue, given by, say, eta is equal to x minus bt, and zeta is equal to x plus bt, then what you can do is you can rearrange this so that you can see that x is the average of zeta plus eta, and that t is 1 on 2b zeta minus eta. That will give you just the t part. And so in particular, the zeta derivative is by the chain rule that we're, of course, getting very good at. Like here. And so the derivative of x with respect to zeta is a half. And the derivative of t with respect to zeta is 1 on 2b. So 1 on 2b and that. And then if we factorize 1 on 2b, what we have is 1 on 2b outside of partial derivative with respect to t plus b times the partial derivative with respect to x. So by making this coordinate transformation, we see that the transport equation is equivalent to the zeta derivative of u being equal to 0. And of course, if you have a function whose zeta derivative is equal to 0, you know that this function does not depend on zeta, it's constant zeta. It is a function of eta alone. Okay, and that's what we see. We see that this is solved by g of eta, and you can figure out what g is given the initial condition, like so. So that's the method of solution by coordinate transformation. Of course, if if you have this formula, someone tells you, or you read it over somebody's shoulder, then you can, of course, check this just by integration directly. So if you have the tth derivative of g of x minus bt by the chain rule, we will have the gradient of g. And what I want to say here is that this is over the space coordinates. All right, we do this often where this gradient, like up here, is only over the space coordinates and the time coordinate is kept separately. Dot product with, oops, that's bt, the partial derivative of x minus bt over the partial derivative with respect to t. And this is, of course, going to give us the gradient of g multiplied by, or dot product rather, with minus b, where this is a vector. And if we take, let's say, the gradient of g, as we should do here, and this is the gradient of g of x minus bt, this will be the gradient of g multiplied by the derivative in the space variables of x minus bt. And this is just going to be the identity matrix. So you just get the gradient of g there. Excuse me. And yeah, so then when you take the dot product of the gradient of g of this form, it is the gradient of g considered as a function of n variables evaluated at x minus bt, for example. Again, making clear this distinction between evaluation of a derivative at a point and the derivative of a composition function where the composition is just shown by a change of variables formula directly substituted in. All right, making again this distinction clear. But anyway, if you then dot product with the second thing by b and then add it with the first thing, then clearly they add up to 0, and we see that this is indeed a solution. So that solves the transport equation with a coordinate change in one dimension, or just with this ansatz in any number of dimensions. We did have a look at what the solutions to this look like, and you can also see this from the formula with g, that this just translates the initial condition, hence the name transport equation. It's just moving backwards and forwards with speed. Sorry, it's moving in a direction with speed given by b, speed and direction given by the vector b. Okay, so now we have the one-dimensional wave equation, which by virtue of being a hyperbolic equation factorizes into two transport operators. Here we have b equals 1 and b equals 1 and b equals minus 1. And what you can do from this factorization is you can solve two problems one after each other. So you look for solutions. Let's say v is equal to 0 of this, and then you look for solutions, that's plus, u is equal to v. So if the first is just a homogeneous transport equation, and then the second is an inhomogeneous transport equation. And you see if you take the second equation and substitute it into the first, you exactly have the one-dimensional wave equation. So u, which is solving this system of equations, also gives a solution to the one-dimensional wave equation. And when you apply this with some initial conditions, you will get D'Alembert's formula here, given in this way. So that's the trick to solving the one-dimensional wave equation, or in general, hyperbolic second-order equations in one space variable will factor, and this technique will apply. So one thing that we do when we have the one-dimensional wave equation is we apply something called Duhamel's principle to this. to get the solution of the inhomogeneous one-dimensional wave equation. All right, here we solve the homogeneous one-dimensional wave equation. So in general, Duhamel's principle, I believe we also use this in the heat equation section to get the solution of the inhomogeneous heat equation. I wanted to apply in a really clear way this principle, so you can see exactly what is part of it, because it's sort of applied very quickly in the script. So what we're going to do now is we're going to do an example where we apply this to get the solution of the inhomogeneous transport equation from the solution of the homogeneous transport equation. In the script, we get the solution of the inhomogeneous transport equation from the method of characteristics, but let's use this other method now, Duhamel's principle, to get that solution. So let me just write the problem we're trying to solve. We are trying to solve, and let's do it in one dimension. So we'll just B times U is equal to F. Of course, you can do it in any number of dimensions. And we have an inhomogeneous term that can depend on X, and it can also depend on T. So instead of trying to solve this problem, what we do is we introduce a parameter S. And we say that for every parameter S greater than 0, we try to solve the following problem. Namely, the homogeneous problem. Maybe I'll write with for the S. Plus B, the X derivative, is equal to 0, homogeneous problem, with the, I don't want to say initial condition, but maybe boundary condition or time condition that when the time is equal to S, the particular parameter, the boundary values, or the initial condition, if you like, is given by the inhomogeneous term evaluated at time S. So what we've seen diagrams that look like this, where we give some initial condition here, and then the solution to the homogeneous problem, or the Dirichlet problem for the transport equation, in this case, gives us the solution on the rest of the space. And what we're going to do is, for every S, let's say for S1 here, we have a problem where we have given the initial data, or we've given what the function should be on this line here, t equals S1, and then we want to solve the homogeneous problem starting from there going forward in time. All right, and we can do this for any other time. Maybe we want to do this for for another time, S2. And so for every parameter S, for every number S, we have one of these problems. Okay, so we can do this. What's the big idea? The idea is, if we add all these together, because we know the sum of any two solutions should also be a solution, but we do something more general. There's infinitely many solutions, so instead of summing them together, we integrate them together. Up to time t, vs t ds. So notice that this is an integral over the parameter s. All right, and so we're integrating the solution to all these different problems together, and the idea is that should give us a solution to the inhomogeneous problem. So this is sort of, where is this coming from? This is coming from the intuition that an inhomogeneous term should be as if you're adding something to the equation. So as if you're putting in extra energy or extra force or something like this as time goes on. And so that's very similar, or there's a parallel there to giving the equation something initially and then letting it go on. So it's like you're giving it initially and letting it go on, but then at the very next time you also give it something extra and let it go on, and then you give it something extra again and let it proceed according to the partial differential equation. And so you add up all these contributions, and you should get the inhomogeneous solution to the inhomogeneous equation. So let's verify that this is actually a solution to the inhomogeneous equation. So firstly, we can just take the derivative in space. There's no problem here. It just passes through the integral. But we can also take the derivative in time. And this formula depends in two places on time. In the limit of the integration, and also as in the function that's being integrated. So we need to apply the rule for that. So that by the fundamental theorem of calculus, when we differentiate the upper bound, you just get the integrand function back at other way around, sorry, s equals to t. Right, so you have to evaluate what's being integrated at the limit, plus then the integral of the derivative, like so. So that's the t derivative of u. And when we add these together, we end up with two things. We end up with vt xt plus an integral of tvs plus b xvs ds. But what do we know about v? Well, we actually know two things about v for every s. We know that it solves the homogeneous problem, so this part is 0. And we know that when the parameter and the time are equal, it's equal to the inhomogeneous term at that particular time. So this gives us f of x comma t. Right, from this, maybe I'll call them A and B, like so. So those two properties apply like that. And what we have, we end up with just the inhomogeneous term. So this shows that U is in fact a solution of the inhomogeneous transport equation. And this idea applies, of course, to other partial differential equations, such as the heat equation and the wave equation. Now, this isn't quite the form, this formula here isn't quite the form that you see it in the script. Why is that? It's because we don't use Vs in the script. We go one step further when we actually give a formula for Vs. So let's do that now, and then we'll see that we get the same formula as in the script. So what is Vs? We should solve this system here. So let me just copy it. We should solve this system. This is the homogeneous transport equation with some initial condition, but the twist or the slight complication is that it's given at time s, it's not given at time 0. So to bring it into the standard form, we make a coordinate transformation or make a time translation. We look at tau, which is t minus s. So when the time is equal to s, when the time t is equal to s, our new parameter tau will be equal to 0, and that's what we want. We also see that the t derivative is equal to tau. So we have that tau vs, the derivative with respect to tau, the derivative with respect to this is equal to 0. and Vs at x when tau is equal to 0 is equal to f of x s. So now, given this coordinate transformation, it is in the form of the homogeneous transport equation with given initial condition. So this is solved by, well, we just have to look above. All right, it's solved by g of x minus bt. So for this situation, it's solved that v of s is equal to f of x minus b tau s. Right, because it's when tau is equal to 0, so it's written in tau. But we can transform this back because we know the relationship between tau and s. So this gives us that v of s is equal to x minus b t minus s. And so let's just be super clear. U is the integral of this. ds. And if we look in the script, what do we have? Whoops, sorry. We have here that it's u, okay, plus some extra initial term for the new initial term is equal to the integral from 0 to t of x plus s minus tb s integrated over s. And here we have minus t minus s. So just manipulating that minus sign, we see that these two are actually the same. So this is how you can use Duhamel's principle to solve the inhomogeneous transport equation. And the same idea applies in general. So what did we do? Just to reiterate, we firstly set up a parameter s, and we looked at a system of the same equation but homogeneous with an initial condition determined by the inhomogeneity, and this depends on s. And then we took the solution to be the sum over s of these solutions to the related problem. And then as a further step, we actually solve those homogeneous problems to get what Vs is. And so then we can write a formula just in terms of the inhomogeneous formula F. But that's the idea of this method. Okay. So there are two things you can generalize from this. One is the method of characteristics and to solve other first order systems. And of course, you can also generalize this to more general wave equations, which we'll deal with next. So the method of characteristics, it's a generalization of the transport equation where you don't have constant coefficients. So here the coefficients in the transport equation were 1 and the different components of B. But what happens if that is not constant anymore? And the idea is to choose a path in the domain where the values of the function can be described by an ODE system parameterized by the initial point. Okay, so what we're going to do is we're going to do this example here. And the idea given by the second thing is that you choose an initial point, let's say x0, y0, and then you consider some path parameterized by s. So this will be x of s, y of s, and consider the function z of s, which is u when x is given by the point along the path and y is given by the point along the path. Consider this function. It's now a function of one variable, but it sort of depends on u here. And what is the derivative of z? How does z change when s changes? Okay, so by the chain rule, I guess I'll call it, it's a function of one variable, so I'll use d. And what we see is for first order systems, or at least linear first order systems, using some nice colors, that if we match these up like this, we can control the behavior of Z along this curve using the information given by the PDE. Okay, so if we choose that dx on ds is equal to x, and we choose that dy ds is equal to 2y, then dz ds is equal to 2y, like so, yeah, by making this choice. And by the PDE, that's equal to u, which is just the function z considered as a function of s rather than as a function of two variables. So what do we get? We get the system of ODEs, d on ds of x, y, z is equal to, not 2x, x, 2y, and z. Okay, so what this does is it reduces a first order equation to a system of ODEs. And then this is a very easy system of ODEs to solve. All right. This system of ODEs is solved by, in this case, x is equal to x0 e to the s, y is equal to y0 e to the 2s, and z is equal to z0 e to the s. Okay, so we can see the dependence on the solution on the initial point. And what is z0? Z0 is nothing but u at x0, y0, like so, which is the value of u at the initial point. So the idea should be if we're given, so this is a solution basically already, right? Like if we're told something about the function u, now we can find about it along other paths like this. Let us see on a graphing program how these characteristics look like. So if we just consider positive parameters, positive values of s, we take the blue point here as our x0, y0, and then we just have the parametric form put into here. So here we have the xy plane, and we see as we move the initial point, we have different characteristics. If we allow the parameter s to take negative values, let's see what that looks like. We sort of see that we have these parabolas that are originating from the origin, or maybe I should say half parabolas, and then in special cases we might have the ray, for example, going off here, the half line, and we also have the vertical half line, and so on. Yeah, so we see that the characteristics cover the entire plane. So for the next step, what we should do is we should consider now some initial values. So suppose we're giving an initial value. And the initial value I have in mind is that is somewhere on the line y equals 1. So if the initial point is always somewhere on the line y equals 1, we can see that the characteristics are going to cover the upper half of the plane, like so. So the well-posed problem here, the one that has a solution and makes sense, would be to consider this partial differential equation on the set xy where y is greater than 0 with boundary conditions u of x1 is equal to 2x squared. Okay, so on this particular line, this green line, we know the values of the function u. And if we know the value of the function for an initial condition, then we know it all the way along the characteristic by solving this OD. This inserted in the wrong spot. One moment. Yes, so if we know the value of the function u on this green line, then by solving this ODE z, which is the values of u considered as a function of s, is equal to the initial value times e to the s, where s is the parameter along that curve. So we can also describe the value of u at anywhere along this blue curve once we know the value at the dot. And we know the value at the dot everywhere on this green line. So that suggests we should choose the initial points for the characteristic, that is x0, y0, to be part of the set where the initial conditions take place. Right? So we're given the initial conditions on the set of all points where x is any coordinate and y is equal to 1. And so we should choose our initial points to lie in this, this boundary. So in other words, i.e., we should take y0 to be equal to 1. And then once we've done this, what do we know? Well, we know that then u at x0, y0, or 1, same thing, is then 2 x0 squared. But we know by definition that z0 is u at that initial point. So z0 is equal to 2x0 squared. So now our system of equations becomes x is equal to x0 e to the s, y is equal to 1 e to the 2s, and z is equal to 2x0 squared e to the s. So what we should do is we should take this system of equations and try to eliminate x0 and s now. Right. We should try to specifically get the formula for z with x0 and s eliminated and it only depending on x and y. So we can see from the second equation that e to the s is the square root of y, and it's the positive square root of y because we're considering the domain y is greater than or equal to 0. And if we make that substitution, then we see that x0 is equal to x on e to the s, which is x on the square root of y. So now we know what e to the s is, which is what we need, and we know what x0 is, so we can say that z is equal to 2 x0 squared, so x on y squared, multiplied by e to the s, which is the square root of y. So when you expand this out, you get 2x squared over the square root of y. And now what we have is z, but instead of it being as a function of s, as it is over here, it's a function of x and y alone. So we can also say that u is 2x squared on z. Because remember, u and z are the same function, except we consider z as a function of s and we consider u as a function of x and y. So once we've done this algebraic manipulation to get z as a function of x and y, then we again write it as u. And then this should be the solution to our partial differential equation. So let's just check that now, because it's always good at the end to check. So if we have x partial x du, what do we have? We end up with 4x squared over the square root of y. Yes. And if we take 2y and then the partial derivative of u with respect to y, so the 2y part is going to give us 2x squared y, and then the derivative of x here is going to give us a negative half 1 over y square root of y, that is y to the negative 3 halves. And there's a 2. All right, that's gives us 4 there actually. And so this is minus 2x squared over the square root of y, because this y cancels with this one. And so when you add these together, you indeed get 2x squared over the square root of y, which is u. And that's exactly what our ODE was, like that. Okay, so that's an example. Let's just recall the steps there. In the first step, you just consider the PDE and you rewrite it into this form of a system of ODEs, and the parameterized curves that you get from this are known as characteristics, and then along the characteristics are parameterized by the initial point, tells you which characteristic you're on, and the S tells you how far along this characteristic you are. And then we have Z as a function of S given its initial value. We then know what Z equivalently this function U anywhere along the characteristic is. So that's the first part. You rewrite the partial differential equation into the characteristics. And then in the second step, you use the boundary conditions that you're given for the problem to relate the initial point x and y and z0 together. And often, by the nature of the boundary conditions, one of the initial points will be determined. And so then it's an algebraic matter of eliminating x0 and the parameters for the initial point and the parameter for along the curve, and getting at the end z equals some function of the space variables x and y, or in other words, getting the solution for u. All right, so those are the two steps for the method of characteristics. One more thing to say is, in the case that it is not a linear first order partial differential equation, as here, or even a quasi-linear one, but it's something more general, then you need to introduce additional coordinates p to sort of work around that. And then instead of having a system of n plus 1, so here that we have 2 dimensions of space plus the function, if you have a nonlinear problem, then you need these p these p variables as well, and then you end up with a system of 2n plus 1 ODEs. But all first order PDEs can be solved by this method of characteristics as well for you to practice with. Okay, so the other way to generalize this is to look at the wave equation, right? So if you think of the transport equation as being the bottom example, then you can go and look at other first order systems, or you can look at wave equations, which are a different generalization. We've already discussed that the wave equation on the real line in one dimension can be solved by D'Alembert's formula. We can use this refraction principle that we already saw when we looked at Green's functions to solve it on the half line. And so the trick for the general case is to put together two things. So to put together the solution on the half line, which ultimately comes from the transport equation, and to put together with spherical means for the wave equation. We already mentioned before the spherical means of the wave equation, they're not constant in R, but they do obey this so-called Euler-Poisson-de-Boer equation in the radius and time. Okay, so here in lemma 5.2, we see that statement exactly, and we see the Euler-Poisson-de-Boer equation here. Notice that it's really not one equation. It's one equation for every dimension of space. This coefficient is different for different dimensions of space, and that turns out to be important. So maybe you would say this is a family of equations, a family of partial differential equations. Yeah. So we've reduced, if you like, the study of the wave equation to understanding the solutions of the Euler-Poisson-de-Boer equation. Now, there are two cases to consider. In odd dimensions, there is a really nice transformation that reduces the Euler-Poisson-de-Boer equation to the one-dimensional wave equation. Let's have a look at that here. In odd dimensions, it is this transformation here. This u tilde is you take u and you multiply it by some r, and then you take some derivatives and multiply them as well. Okay, maybe it's not that nice, but at least it's a nice closed, it's not too bad. And that transforms the Euler-Poisson-de-Boer equation into an ordinary one-dimensional wave equation. However, because the radius is only defined for positive r, it's a one-dimensional wave equation on the half line. But that's okay, we know how to solve that. So that handles all the odd dimensions. For the even dimensions, there is no such transformation that reduces the EPD to the wave equation. However, what you can do is the following observation, and this is an observation that we saw for plane waves, is that if you have a solution to the wave equation in a lower dimension, you can take the same formula and consider it as a function in higher dimensions, constant in the new variables, and then this is a solution to the wave equation in higher variables. Okay, and this is called extending the solution to higher variables. And this is the idea of the method of descent. So in even dimensions, extend the solution to one dimension higher. So if you look again in the script, this is this operation here with into n plus 1, where you add here, and it's all these functions with bar. Okay, these functions with bar means the extended solution in the higher dimension. I think this is explained in dimension 2. All right, that the function u bar is a function in R3 that is just u bar is equal to u and you ignore the third coordinate. Basically, that's what x bar is saying. Ignore the third coordinate. And then when you do that, what you have is you have now a wave equation in odd dimensions where your boundary value conditions do not depend on the last coordinate. And so now you go through and you apply your method of solution for odd dimensions and you get some solution. And because the initial conditions do not depend on the last coordinate, your solution does not depend on the last coordinate either. So it's constant in the last coordinate. That means it actually solves the wave equation in one dimension lower. And so now we have our solution in one dimension lower that we actually wanted in the even dimension. If you'll see from exercise 44, where we actually go through this, these transformations that you apply at each step, they don't only change the partial differential equation, they also change the initial and boundary conditions. This is needed because when you start here in even dimensions, change to odd dimensions, change to the Euler-Poisson de Boer equation, change the one-dimensional wave equation on the half line. To write down the solution to the equation on the half line, you need to know the boundary conditions, so you need to transform the boundary conditions at every step as well. All right, so that then you can put them in the modified D'Alembert formula. And then undo all the transformations and get the solution back at the end. So I think this is really well covered in exercise 44. So I just wanted to give a summary of those steps again. And those are all the methods of solutions that we covered in this course.